Object-oriented programming is one of the most powerful and flexible approaches to building large, maintainable software systems. In Python, classes and objects allow you to group related data and functionality into reusable components that reflect real-world structure. Whether you're modeling users, transactions, or time intervals, Python classes help you write clearer, more organized, and more scalable code. This video will guide you through the core ideas behind Python's object-oriented model, how to define classes, work with attributes and methods, and customize behavior through built-in features like constructors and operator overloading. If you're already comfortable with lists, dictionaries, and functions, learning classes is the next logical step in building professional-grade Python programs. Understanding Python classes and object-oriented programming by the Programming Professor. This video begins with an overview of what you'll learn: how to define your own classes, group data into objects, and implement instance methods. We'll cover the distinction between class and instance objects, explore constructors and interfaces, and examine how to customize class behavior through special methods. You'll also learn how Python handles memory allocation and garbage collection behind the scenes. By the end, you'll be ready to create your own classes and use them to write cleaner, more modular, and more maintainable Python code. Programs, like the world around us, are composed of smaller components grouped into meaningful units. Just as a chair combines wood, screws, and fabric, or a TV integrates glass, circuits, and plastic, software brings together variables and functions into cohesive objects. Object-oriented programming reflects this structure by allowing us to build systems out of these grouped elements. In Python, objects contain both data, called attributes, and the operations that work on them, called methods. By bundling related variables and functionality, objects help reduce complexity and improve clarity. They make it easier to reason about programs as they grow larger. This principle of grouping related parts into reusable, self-contained units is what makes object-oriented programming so powerful. A core principle of object-oriented programming is abstraction, the idea that users interact with an object without needing to understand its internal workings. Consider an oven. You interact with its dials and display, not the wires and heating coils inside. In programming, this is called information hiding or encapsulation. Objects expose public methods and hide internal data, protecting implementation details from external interference. This leads to cleaner, more modular code that's easier to test and maintain. Python supports this through conventions and controlled attribute access. When you define a class, you can encapsulate data and expose only the operations needed to use it safely. This forms the basis of an abstract data type, or ADT, an object defined not by how it works internally, but by the operations it supports. Python is an object-oriented language at its core. Even the most basic data types, like integers, strings, and lists, are implemented as objects. Each of these objects carries both data and behavior. For example, a string not only stores text like hello, but also provides methods like .lower to transform that text, or .isDigit to analyze it. This means that Python programs are constantly interacting with built-in objects, whether you realize it or not. You can define your own classes in exactly the same way, creating new types of objects tailored to your program's needs. Once you start thinking in terms of objects, you'll see how Python's design encourages reuse, structure, and extensibility through its class-based model. Classes give you a way to group related data and behavior into a single, reusable structure. Instead of managing multiple related variables separately, like hours and minutes, you can define a class, such as time, that contains both as attributes. In Python, you define a class using the class keyword, followed by the class name and a colon. Inside the class body, you write statements that describe the object's structure, like assigning default values or defining functions that operate on the object's data. This approach allows you to create your own custom data types that behave in structured, predictable ways. Think of a class as a blueprint. It defines what data and behavior the object should have, but you still need to create actual instances to use it in your program. When you define a class, you can include attributes, variables that store data about each object. To initialize those attributes, Python uses a special method called init, also known as the constructor. This method is automatically called when you create a new instance of the class. For example, a time class might define self.hours equals 0 and self.minutes equals 0 in the constructor to establish initial values. These attributes become part of the object and can be accessed or updated later. The use of self ensures that each object has its own independent data. This pattern, defining data with attributes and initializing them using init, is the foundation of class design in Python. Once you've defined a class and its attributes, you can create instances, individual objects based on that class. Instantiating a class is done by calling the class name with parentheses, just like a function. For example, my time equals time creates a new time object. This automatically calls the init method, which sets the initial values for that instance. You can then access or modify attributes using dot notation, such as my time.hours equals 10. Dot notation is also used to call methods associated with the object. A helpful convention is to use initial capitalization when naming classes, such as lunch menu, PDF file, or coin amounts, while using lowercase for instance variables. This helps distinguish user-defined types from regular variables in your code. Classes don't just hold data, they also define behavior using instance methods. These are functions written inside the class that operate on the object's data. Instance methods are always defined with self as the first parameter, which represents the specific object the method is being called on. You invoke instance methods using dot notation. For example, time1.printtime calls the printtime method on the time1 object. This method might then access self.hours and self.minutes to display the current time stored in that instance. By packaging both data and logic into a single object, you improve modularity and readability. Instance methods are how your objects do things, and they form the interactive interface between objects and the rest of your program. It's important to understand how Python treats certain methods as special, particularly init, which is automatically called when creating an object. These special methods, sometimes called dunder methods because they have double underscores before and after their names, let you hook into Python's object system. You should avoid using double underscores in your own method names to prevent conflicts. A common beginner mistake is forgetting to include self as the first parameter in an instance method. When you omit self, Python still tries to pass the object automatically, which results in a too many arguments error. The rule is simple. Always include self as the first parameter in every method you define within a class, but don't include it when calling the method on an object. It's passed automatically. A class in Python is a blueprint for creating objects, but the objects themselves, called instances, are the actual usable entities in your program. When you define a class, you're describing the structure and behavior of a new type. When you call the class name with parentheses, Python creates a new instance of that class. Each instance is independent and can hold its own data. For example, a time class might define attributes for hours and minutes, but each time object represents a specific point in time. Understanding the difference between a class and an instance is crucial. The class defines what the object is, and the instance is the actual thing you work with in your code. Classes and instances each have their own attributes. Class attributes belong to the class itself and are shared across all instances. They're defined directly inside the class body, outside of any methods. Instance attributes, on the other hand, belong to individual objects and are typically defined inside the constructor init, using self. For example, you might define a class attribute species equals human for all person objects, but each person instance has its own name and age attributes. This distinction allows you to create default or shared data at the class level while keeping unique data at the instance level. When you access an attribute on an object, Python first looks for it on the instance. If it doesn't find it there, it looks at the class, and then at any parent classes in the inheritance chain. This is called the attribute lookup order. It allows classes to define default values or behaviors that instances can override. However, you should use this power thoughtfully. Avoid changing class attributes through an instance, as this can cause confusion. Instead, modify class attributes at the class level and instance attributes at the instance level. This separation keeps your code predictable and easier to maintain. The constructor in Python is the init method. It runs automatically whenever you create a new instance of a class and is used to set up the object's initial state. Inside init, you define parameters that accept data from outside and assign them to self-attributes to store them in the object. For example, a time constructor might take hours and minutes as parameters and assign them to self.hours and self.minutes. Constructors make it possible to create fully initialized objects in a single step and ensure your objects start with valid, predictable data. A common pattern in Python classes is to pass information into the constructor and immediately save it as instance attributes. For example, you might define init of self, name, and age, and then store those values with self.name equals name and self.age equals age. This approach makes your object self-contained and easy to work with. Each instance can be created with its own data without needing additional setup calls after creation. This pattern is considered best practice because it clearly communicates what data the object needs to function and ensures all objects of that class start in a consistent, usable state. Python allows you to define default values for constructor parameters, just like you would for regular functions. This makes your classes more flexible and easier to use. For example, in an employee class, you might set the default wage to 15.50 and hours per week to 40. This means the user only has to provide a name when creating an instance, and the other values will default unless explicitly overridden. Using default values reduces repetition, allows for more concise instantiations, and is a great way to handle common or typical cases while still leaving room for customization. When calling a constructor with default parameters, Python allows you to mix positional arguments and named arguments. However, there are some rules. Positional arguments must come first, and required arguments must always be provided. After that, you can specify any optional arguments using their names. For example, you can create an employee with Tracy as the input argument, override the wage with employee with both Jordan and wage equals 20 as argument, or specify both optional values with employee with Alex, wage equals 18, and hours per week equals 30 as arguments. This flexibility makes object creation cleaner and more readable, especially when your class has several optional parameters. The interface of a class refers to the set of methods that are intended to be used by programmers who work with instances of that class. For example, a racetime class might include methods like printtime or printpace. These are public-facing methods that users are expected to call. They define how the object should be used and what capabilities it exposes. The clearer and more consistent your class interface, the easier it becomes for others, or your future self, to understand and work with your code. Designing a good interface means clearly separating public methods from internal implementation details. Not all methods in a class are meant to be used directly by the end user. Some are internal helper methods used only within the class to support public methods. In Python, it's common practice to indicate this by prefixing the method name with a single underscore, for example, difftime. This is a convention, not enforcement. It signals to other programmers. This method is internal, don't call it directly. A well-designed class uses internal methods to hide complexity and keep the public interface clean. This separation of interface and implementation makes your class easier to maintain and less prone to misuse. A class in Python can be used to implement an abstract data type, or ADT. An ADT defines a data structure by the operations you can perform on it, not by how it's implemented. For example, the racetime class might define operations like printtime and printpace without exposing how those results are calculated. The user interacts with the object only through the public methods, while the internal workings are hidden. This kind of design makes your code more modular and allows you to change the implementation later, such as improving performance or accuracy, without breaking the rest of your program. One of the cornerstones of object-oriented programming is the separation of interface from implementation. The interface is the set of public methods and attributes you design for users to interact with. The implementation includes everything under the hood: how those methods actually work, internal logic, helper methods, and private data. Python doesn't enforce strict privacy like some other languages, but it relies on convention. You can still access any attribute or method, even if it's meant to be internal. That's why naming conventions, like prefixing internal methods with an underscore, are so important. They signal to other programmers what should and shouldn't be touched. A clear interface helps prevent accidental misuse, improves readability, and keeps your code modular and maintainable. Python allows you to customize how your objects are displayed by defining the special str method in your class. This method controls what gets printed when you use print on an object. Without it, Python just shows a generic string like main.toy object at 0x ... which isn't very helpful. By implementing str, you can return a human-readable string, for example, describing a toy's name, price, and age recommendation. This makes debugging, logging, and user-facing messages much more meaningful. It's one of the simplest ways to improve the usability and professionalism of your class. Python gives you the ability to define how your objects behave with comparison operators, like less than. You do this by defining the LT method in your class, which stands for less than. For example, in a time class, you can compare two instances based on their hours and minutes. This allows you to sort a list of time objects or find the earliest time using built-in functions. Operator overloading like this makes your custom objects work more like native types, which improves integration with other code and makes your classes feel more natural to use. Beyond just less than, Python supports rich comparison methods that let you customize the behavior of all major comparison operators. These include LE for less than or equals, GT for greater than, GE for greater than or equals, AQ for equals, and NE for not equals. You don't have to implement all of them, just the ones that make sense for your class. For example, if your object has a natural order, you might implement less than or equals, and equals. These methods let your objects integrate seamlessly with Python's sorting and comparison tools. They also support clearer, more intuitive expressions in your program logic when working with custom types. Python lets you go even further by overloading arithmetic operators, turning your classes into numeric-like types. You can define methods like add, sub, mul, and trutive to customize how objects behave when used with plus, minus, multiply, or divide. For example, a time24 class might implement subtraction to find the shortest time difference between two times, accounting for wrapping around midnight. This lets you write expressions like t1 minus t2 and get a meaningful result. By overloading operators, you're teaching Python how to apply built-in syntax to your custom types, which can lead to more natural and expressive code. When you overload operators like subtraction, it's important to handle different types of input gracefully. Python's built-in is instance. Function helps with this by checking whether an object matches a specific type. For example, in a time24 class, you might allow subtraction between two time24 objects, or subtract an integer representing hours. Inside your method, use is instance of other and int or is instance of other and time24 to decide how to handle each case. This lets you support multiple behaviors within the same method while still writing safe, type-aware code. If the input doesn't match any expected type, you can raise a type error to inform the user. This is a powerful way to make your classes more robust and user-friendly. Python gives you the ability to customize nearly every numeric operator through special methods. Want to support addition? Use add. Subtraction. That's sub. You can also overload mul for multiplication, trutive for division, and even florative, mod, and pow for more advanced math operations. If your class represents something numeric, like time, temperature, distance, or currency, you can use these methods to make your objects behave just like numbers. Python also supports logical operators and/or, as well as conversion functions like int and float. You don't have to implement all of them, just the ones that make sense for your object's behavior. You can make your objects work with Python's built-in functions like abs, int, and float by defining their corresponding special methods. For example, implementing float in a temperature class lets you convert a temperature from Celsius to Fahrenheit when calling float of mytemp. Similarly, int could round or truncate the value. These hooks allow your objects to integrate with Python's built-in type system and standard library functions. This makes your custom types more flexible and compatible with existing Python tools, allowing them to plug into calculations, comparisons, or conversions with ease. Behind the scenes, Python handles memory allocation so you don't have to manage it manually. When you create variables, lists, objects, or any other structure, Python automatically requests and organizes memory from the operating system. In contrast to low-level languages like C or C++, where programmers have to explicitly allocate and free memory, Python handles this automatically. For example, if you append 100 items to a list, Python dynamically resizes and manages the required memory. This abstraction allows you to focus on writing logic, not worrying about where data lives in memory. It's a major benefit of working in a high-level language. Just as Python allocates memory automatically, it also frees it when it's no longer needed. This is done through garbage collection, a process where Python tracks how many references point to each object. If an object's reference count drops to 0, meaning nothing is using it anymore, it becomes eligible for deallocation. Python's garbage collector then reclaims the memory, making it available for future use. This allows your programs to run efficiently without manual memory management. Keep in mind that while Python handles garbage collection for you, the exact timing may vary slightly depending on the Python implementation and environment. In this video, you've learned how Python supports object-oriented programming through classes and objects. You saw how to define custom classes using the class keyword, how to use constructors to initialize objects, and how to store data in instance attributes. You explored the difference between class-level and instance-level attributes and learned how Python handles attribute lookup. We discussed the importance of designing a clean class interface, using public methods to expose functionality and internal methods to hide implementation details. You also saw how to customize object behavior with special methods like SDR, LT, and add, allowing your classes to work naturally with Python's built-in syntax. Finally, we covered memory management, understanding how Python allocates memory automatically and cleans up unused objects through garbage collection. Altogether, these concepts allow you to create more modular, reusable, and real-world-oriented Python code. Object-oriented programming gives structure to your logic and helps you model systems more effectively. As you apply these ideas to your own projects, you'll find that classes make your code easier to manage, extend, and maintain, especially as programs grow in size and complexity. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.